Hello everyone. This week's QTFMS talk will be given by Jun Madea from Kyoto University. He's going to talk about his recent work on twisted partition functions as order parameters. Jun, thanks a lot for accepting the invitation. You can take away.
Okay, thank you for the introduction, and thank you for giving me an opportunity to talk in this seminar. I'm Jun Maeda from Kyoto University. So the title of my talk is Twisted Partition Functions as Order Parameters. This is a collaboration with Yuya Tanizaki in YITP. And yeah, he also talked in this seminar 3 weeks ago, I think. But anyway, let me start on my talk. When we want to detect the SSA phase, we usually use order parameters. So we introduce symmetry breaking field and we evaluate one point function of order parameter. Then we take in large volume limit, and after that, we take h to zero limit, where this h is a symmetry breaking parameter like magnetic field. And or if you do not want to introduce symmetry breaking field, you can use the method of diagonal long-range order. In this method, we evaluate connected two-point function of order parameter, and we take the large distance limit. And yeah, in this method, if this value is non-zero, then we find the system is in the SSE. So these methods are standard methods to detect SSE phase. However, in this talk, we instead consider as a method the twisted partition function, which is a partition function with a background gauge field for some symmetry. And yeah, for continuous symmetry case, the twisted partition function is defined by this form. So because there is a conserved current, so we can define this just as coupling the background gauge field to the conserved current. Then what is the physical meaning of the twisted partition function? For non-flat field, which is a field with non-zero field strength, then this is just equivalent to the insertion of electric flux or magnetic flux, because each component of field strength is electric field or magnetic field. And yeah, for flat field, which means a field with zero field strength, then one may wonder there is no degree of freedom. But actually, there is a degree of freedom of holonomy of gauge field, and it is equivalent to imposing the twisted boundary conditions. Um, Yes, to consider twisted boundary condition, we must compactify the spacetime. So, and in this talk, we especially focus on torus, d-dimensional torus as a spacetime. So this beta is inverse temperature, which means the length of the temporal direction, and this L is length of the spatial direction. Let us consider the following example of U1 flat gauge field, which is written as this form. Then, yeah, this is constant gauge field, so its field strength is zero, and therefore this is a flat field. And actually, we can eliminate this gauge field A by gauge transformation with parameter lambda to be this form. So gauge transformation is given by this, and then we do a gauge transformation with parameter lambda to be this one, then we can eliminate it. But the price we have to pay is that we must impose twisted boundary conditions for matter field. So in this sense,
Hi, I have a
yeah,
question. I just want to clarify. In your expression for the gauge field, what is that expression exactly? Alpha dt by beta? Is
uh,
is that like a one form? Is that what you're doing?
this is a one form. So uh, the temporal direction, the coordinate of the temporal direction is denoted by t, and yeah, this is
Right.
just a usual differential form.
Okay. And I missed the very beginning. So did you define what exactly a twisted uh, boundary
Uh,
condition is?
it's twisted mean, you can understand twisted boundary condition just, this is a definition. So, So, for example, let us consider complex scalar field theory. Then there is a symmetry of U1 symmetry of phase rotation of phi. And yeah, here we compactualize the space-time. So usually we choose periodic boundary condition for field, but instead here we impose this boundary condition. So this is a definition of the twisted boundary
Oh,
condition.
okay. Okay. Got it. Thanks.
Yes, and thank you for the question. Okay, so yeah, this is a case of continuous symmetry. And then what about the discrete symmetry? For discrete symmetry, there is no Lie algebra and there is no conserved current. So we cannot define the twisted partition function by this equation. Yeah, but there is a symmetry twisted boundary condition even for discrete symmetry case. So it means gauge field for discrete symmetry is always flat, and the twisted partition function is just a partition function with twisted boundary conditions. Okay, so let us consider this example. We consider real scalar field theory, and this theory has this symmetry which acts on phi as flipping sign, and so we can consider this gauge field. And here the spacetime is d-dimensional torus, so we can consider d types of holonomy along each cycle. And it means this gauge field can be regarded as an element of this power of this. So, for example, if we take A to be 1, 0, 0, 0, then this is equivalent to imposing the twisted boundary condition along the temporal direction, like this one. So phi t plus beta equals to minus phi t.
I have another question.
Okay.
So for a discrete symmetry, right, the gauge field is always flat.
Yeah.
But then are you saying that the boundary conditions are twisted because because you have a discrete symmetry, or you're
Uh,
saying that?
uh, so here, I mean, so for non-trivial gauge field, it is equivalent to import twisted boundary condition. So here, there are D component uh, of A, and when AT, a component of A along T direction is non-trivial, then we must impose twisted boundary condition along
I see, I
the
see.
direction. But other direction, we impose a periodic boundary condition.
So the point is that if you want to have a non-trivial gauge configuration um, for a discrete gauge field,
Yeah,
then you must impose twisted boundary conditions.
yeah. So
Is that
uh,
right?
yeah, right. So
Okay.
it is the same as this kind of situation. So uh, for even for a continuous symmetry case, then if we consider flat gauge field, then it is always have like this form, and we can eliminate the gauge field, but we must import twisted boundary condition instead. So
Okay.
yeah,
Thank you.
here and yeah, discrete symmetry case is also we can do similar way. Okay, so yeah. Then we want to consider the following question. How does the twisted partition function behaves in the IR? So let us consider this example again. And this theory has two gapped phases. So one is for positive V scale, this system is in the SSA phase of this symmetry. While for negative V scale, this system is in the trivial phase with unique gapped vacuum. So the question is, how does the behavior, how does the twisted partition function behaves in each phase, SSA phase and trivial? First, we consider SSA phase case. So in SSA phase, there are two potential minima, which is represented by this phi x equals to plus minus v, and this constant configuration are not compatible with twisted boundary condition because twisted boundary condition flips sign. So plus v flips to minus v and minus v flips to plus v. So the constant configuration like this form is not compatible with twisted boundary condition. Instead, we must connect two minima plus v and minus v by some kink contribution. And kink is extended to the spatial direction, whose volume is L to the d minus 1, and also kink has a tension. Therefore, the ratio of the twisted partition function shows exponential decay. So because the twisted partition function is dominated by this kink contribution, and then it shows exponential decay. And then we take large volume limit and we get the vanishing behavior of the twisted partition function. So yeah, to summarize, the ratio of the twisted partition function behaves like delta function of A in SSA phase. So here delta function is defined by this equation. So for A equals 0, then it takes value 1, and otherwise it takes value 0. So this is a behavior in SSA phase. Then what about trivial phase? In trivial phase, there is one potential minima. So this is written by phi x equals to 0. And this is compatible with any twisted boundary condition. Then, yeah, this implies that twisted partition function does not have dependence on any twisted dependence on twisted boundary conditions, or equivalently does not have dependence on gauge field. And so the twisted partition function behaves like constant functional in trivial phase. So yeah, behavior of the twisted partition function in each phase is given by this. It behaves like delta functional in SSA phase and constant functional in trivial phase. So they show the different behavior in each phase. Therefore, we can use the twisted partition function to diagnose SSP phase and trivial phase. This is a easiest example of such kind of analysis. So we want to extend this argument to more general phase. So the question is, what kind of phases can the partition function diagnose? So to answer this question, in my talk, we consider several phases. The first part of my talk is about wrapped phases with discrete symmetry. Especially, yeah, first we focus on SSA phase and SPT phase case, and then I will explain SET phase. And the second part of my talk is about SSA phase of continuous symmetry. First, I will calculate the partition function explicitly in the case of one symmetry breaking case. And then I will explain the perspective from mixed anomaly. Okay, so the outline of my talk is as follows. Okay, let us move on to the discrete symmetry case. Okay, let us consider a phase where discrete G symmetry is broken to a subgroup H. And we introduce a background gauge field for G symmetry. So each component of A is an element of G. And in this phase, in partial SSE phase, when AI is not an element of H, then domain wall must appears. So domain wall is extended to the world volume perpendicular to the ith direction if AI is not an element of H. This is because so H is unbroken symmetry. So when AI is not an element of H, twisted boundary condition flips one vacuum to another vacuum. So we must connect these vacua by some domain wall-like configuration. Then twisted partition function shows exponential decay. So yeah, this implies that the twisted partition function is non-zero only when all AIs are element of H. Otherwise, domain wall appears and the twisted partition function vanishes. Yeah, so the twisted partition function behaves in partial SSA phase as like this form. So when A can be regarded as H-valued gauge field, it takes values 1, but otherwise it takes values 0 because of the domain wall-like configuration. So this is a behavior of the twisted partition function in general SSA phase of discrete symmetry. Then let us consider SPT phase case. SPT is an abbreviation of symmetry-protected topological phase. And GSPT phase is a phase with G-symmetric unique gapped ground state. So if we forget G-symmetry, then it is a phase with unique gapped ground state, so it is almost trivial phase. But if you remember the information of G-symmetry, then this system may have a non-trivial topological response with respect to gauge field for G-symmetry, like this form. So the point is it takes values in U1. So it does not vanish because GSPT phase is a phase with unique gapped ground state, so there is no degenerate vacua. So there is no summation here. And then the partition function takes values in U1. This is a point. And actually, the form of alpha is constrained by locality and flatness of A. And it is known that alpha is classified by some group cohomology or Boltzmann group in mathematical language. But yeah, this is somewhat abstract, so I will give an example. So let us consider SPT phases in 4D, which is protected by ZN one-form symmetry. And so here, this one means one-form symmetry. And SPT phase is protected by ZN one-form symmetry is characterized by this Boltzmann group, which is equivalent to ZN. So it means SPT phase is labeled by some element of ZN. And the explicit form of the twisted partition function is given by this in this case. So here, this is a cup product. Yeah, but if you do not know, yeah, you can understand this as just as a ordinary wedge product. And so there is no big difference. And so yeah, this is a typical behavior of the twisted partition function in SPT phase.
Can I ask a question?
Yeah, okay.
Can we say that there is a relation between the anomalies in three-dimensional theories with ZN one-form symmetries and the SPT phases in four dimensions?
Yeah. Anomaly can be understood as anomaly inflow mechanism, and in this mechanism, anomaly can be understood as a one higher dimensional SPT phase.
Ah, I see. So it's directly related
Yeah.
to anomalies in one lower dimension. Okay.
Yeah. Yeah, so I explained SSA phase case and SPT phase case, but we can more we can consider more general gapped phase, just combining SSA phase and SPT phase. And actually there is another possibility of SET phase, but I will explain SET phase later. So here I will focus on gapped phases except for SET phase. And general gapped phases of discrete Jun symmetry, except for SET phase, is classified by unbroken symmetry H and SPT phase labeled by this group cohomology. And yeah, here we consider SSE phase with whose unbroken symmetry is H. So each vacuum has only H symmetry, not G. So here we must consider that SPT phase is not labeled by group cohomology of G, but this should be H. And in this phase, the twisted partition function behaves like this form. This can be obtained by just combining the previous result. Yes, because here this is a partition function of SSA phase in such case. And this is a SPT phase partition function. So uh, in general gapped phases of discrete symmetry, twisted partition function behaves like this form. Okay. So is there any question or comment? Okay, if not, let's move on to an example. So let us consider 4D SNGS theory. And this theory has Gn one-form electric symmetry, which is often called as center symmetry. And there are n-squared line operators generated by fundamental Wilson line and fundamental Hooft line. And it is known that gapped phases of the gapped phase of 4D SN theory is characterized by n-deconfined line within these n-squared line operators. And it is usually called Wilson to Hooft classification. So for example, confinement phase is the N1 form symmetric phase. And this phase is characterized by perimeter law of two-Hooft loop. We usually consider area law of Wilson loop to detect confinement phase, but precisely speaking, we cannot determine gapped phases by only area law of Wilson loop. So we should consider which kinds of lines are obeying perimeter to detect the gapped phases. And confinement phase is the N1 form symmetric phase, so twisted partition function behaves like a constant function. And the confinement phase is the N1 form SSA phase. So in this phase, the N1 form symmetry is completely blocked. And it is characterized by a perimeter of Wilson loop. And since this is a SSA phase, and the twisted partition function behaves like a delta function. Okay, so these are fundamental gapped phases for the SNJ theory, but we can consider more general gapped phases because as I explained here, there are SPT phases in 4D protected by the N1 form symmetry, so we can consider such phases in the case of 4D SNJ theory. And such phases are called oblique confinement phases. So this phase is the N1 form SPT phase labeled by some element of the large N. And the twisted partition function behaves like this one, as I explained before. And this phase is characterized by perimeter law of line operators generated by this combination of lines. So usually confinement phase is characterized by perimeter loop to Hooft loop, but here this oblique confinement phase is characterized by perimeter loop this kind of dionic loops. So it means in oblique confinement phase, not monopole, but dion condenses. Thus, this phase is called as oblique confinement phase. And yeah, of course,
Can I ask a question about exactly
sure.
this point? Is this what happens in Seiberg-Witten theory?
So
Because I
yeah,
think ions condensate in one phase. Would that be
uh,
oblique confinement?
I think so, but I'm not familiar with cyber theory, so I cannot
Ah, okay.
say something correct statement. But yeah, I think so.
Okay. Okay. Thanks.
Yes, thank you for question. And yeah, we can consider more general gapped phases. So in 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 this phase, the large n1 form symmetry is spontaneously broken to the small n, and also it is characterized by the small n SPD phase, which is labeled by element of the small n. And the behavior of the twisted partition function is like this one. So this is the partition function of SSA phase, and this is a partition function of SPT phase. And it is this phase is characterized by perimeter lobe of line operators generated by W to the N and this combination. Yeah, so we can understand gapped phases of 4DSN gauge theory by Wilson to Hooft classification, or yeah, it can be understood by the behavior of the twisted partition function. Mhm. Yeah, so is there any question or comment? Okay, then I will explain symmetry-enriched topological order phase, which is usually called SET phase. SET phase is characterized by anionic excitation. Yeah, precisely speaking, topological order phase is characterized by anionic excitation. And so in topological order phase, ground state degeneracy depends on space manifold because of this anionic excitation. And G GSET phase is GSET phase is a topological order phase, and it is also characterized by this property. Anyons of topological order have fractional charge under Z symmetry. And the classification of GSET phase is well studied in this paper, and the statement of this paper is given a one topological order, then GSET phase is labeled by element of this group cohomology. So here G is a G symmetry, and this calligraphy A is a set of abelian anyons, uh, which means abelian anyons is anyon whose quantum dimension is 1. And yeah, so what is the physical meaning of this alpha? Physically, so when we want to, sorry, when we place G defects labeled by GH and consider fuse two defects fuse into GH, like this figure, then there is a junction of G defects, and this alpha means anion labeled by alpha GH appears at the junction of these G defects. Okay, so yeah, and what is the behavior of the twisted partition function in this SAT phase? First, topological order phase can be regarded as an SSA phase of one-form symmetry. So, yeah, this one-form symmetry is a symmetry of anyons, and here actually we consider 2 plus 1D. So, the anion lines are topological, so it means there is a one-form symmetry. And actually, topological ordered phase can be regarded as an SSA phase of such one-form symmetry. Then we denote a gauge field for one-form symmetry by B. Then twisted partition function behaves like a delta functional in terms of B. And in SET phase, labeled by alpha, since anyone labeled by alpha GH appears at the junction of G defects, B and here B is here one form gauge field B and gauge field A for G symmetry is related by this relation. So we can understand this as follows. So B is a gauge field for one form symmetry and symmetry defects are anyons. So the data will be is equivalent to the position of anyons. So anyon appears at the junction of G defects means such kind of relation. And substituting this expression for this, then we obtain the behavior of the twisted partition function in SET phase. And the point is that unlike the case of SSA phase, usual SSA phase, in SET phase, twisted input of the delta functional is a quadratic for A. For the case of SSB phase, input of the delta functional is just linear of A, but here this is a quadratic. And therefore, it means let us consider again SSA phase case. In SSA phase case, we put defect or equivalent. We import Cecil boundary condition, then domain wall appears. But in SET phase case, we must place G defects so that there is a junction. And then anyon must appear and the partition function shows exponential decay due to the appearance of anyon. So here this should be a quadratic function of A. Okay. So is there any question or comment? Okay, if not, let's move on to the case of continuous symmetry. For continuous symmetry, there are two difference points from the SSB of discrete symmetry. First one is there are Laplace Nabor-Goldstone mode in SSB phase of continuous symmetry, and there is no sharply localized domain wall. In the case of discrete symmetry, the behavior of the twisted partition function comes from the domain wall contribution. So this implies the behavior of the twisted partition function in SSA phase of continuous symmetry should differ from that in the case of discrete symmetry. And the second point is that for continuous symmetry, we can consider non-flat background gauge field. For discrete symmetry, gauge field is always flat, but for continuous symmetry, we can consider non-flat gauge field, which is equivalent to the insertion of electric flux or magnetic flux. Okay, first I will explain the calculation of the partition function in human symmetry case. Low energy effective theory of human SSA phase is described by S1 nonlinear sigma model. The action is like this. And in terms of S1 nonlinear sigma model, broken human symmetry is described by a shift symmetry of phi. So this pi is a number Goldstone mode. And we can introduce U1 background gauge field. And yeah, I will calculate the partition function explicitly. First, we consider a flat background gauge field, which is written as this form. And to calculate the partition function, we must express phi as a sum of winding part and the fluctuation part. And substituting this for the this partition function, we obtain the following result. So fluctuation part becomes the fluctuation determinant, and the winding part becomes this form. And from this expression, we find the twisted partition function vanishes in the large beta and the large L limit uh, if the this scale separation is satisfied. Because here v squared to the d minus 1 over beta appears in the exponential. So yeah, only if this scale separation is satisfied, then the scale partition function vanishes. Then what is the physical meaning of this scale separation? Uh, First, let us consider the right-hand side. The most right-hand side, 1 over L, means it is energy of particle-like Laplace excitation. Because here we consider finite volume with the length L. So the energy of particle-like Laplace excitation is approximated by 1 over L. And yeah, therefore, this inequality means that we want to neglect particle-like Laplace excitation because inverse temp, yeah, we states above the states with energy above the 1 over beta is projected out. So this inequality means we want to neglect particle-like Laplace excitation, and we just want to take into account only of vacuum contribution. And yeah, then what about the left-hand side? So this value, the most left-hand side, this value is splitting energy of vacuum. So here we consider U1 SSE phase, so there are S1 vacua, but these S1 vacua are splitted in finite volume. And the splitting energy is given by this form. We can derive this by using Poisson summation formula like this. But anyway, so this value represents energy of splitting energy of vacua. So this left-hand side inequality means that we want to include enough amount of vacuum states. And if not this inequality, is satisfied, then yeah, we cannot take into account of enough amount of vacua, so we cannot derive the correct behavior of the twisted partition function. So this is a physical meaning of the scale separation, and if this relation is satisfied, then twisted partition function vanishes in the large volume limit and the low temperature limit. So this is a flat field case. Then I will explain the non-flat background gauge field case. Here we introduce U1 non-flat background gauge field with this relation. This means we insert the unit magnetic flux. And in the presence of magnetic flux, no vortex configuration is prohibited, and the vortex excitation must appear. However, we consider low energy effective theory. So in terms of S1 nonlinear sigma model, vortex has infinite energy and it should be regarded as a defect. So this means that the partition function must exactly vanish. So yeah, there is a different point from the case of flat gauge field. For flat gauge field, the partition function vanishes in the large volume limit, but at finite volume, this partition function has a finite non-zero value. But for non-flat gauge field, the partition function exactly vanish at the finite volume. So this is a difference. Okay, so this is a symmetry case, but yeah, of course we want to consider more general SSA phase of continuous symmetry, but it is difficult to calculate the partition function explicitly for the case for more general case. So uh, so we will take another approach. So the question is, can we derive some conditions when the twisted partition function must vanish? Because yeah, the typical behavior of the twisted partition function is vanishing behavior. So I want to derive some condition when the twisted partition function must vanish. We should note that here vanish means exactly vanish at finite volume. Yeah, so can we derive, we want to derive some condition for vanishing behavior at finite volume. And we find the answer is that we can derive the condition by mixed anomaly between the broken symmetry and the solitonic symmetry. So first I will explain what is a solitonic symmetry. So, in SSA phase, topological soliton often appears. For example, domain in SSA phase of discrete symmetry, domain wall appears, and in SSA phase of U1 symmetry, vortex often appears. And charges of topological solitons are protected by some homotopy group. For example, domain wall is protected by pi zero of symmetry group, and charge of vortex is protected by pi 1 U1. And so in general, charges of topological soliton are protected by some homotopy group. And yeah, the conservation of charge means there is some symmetry, and we call the corresponding symmetry as a solitonic symmetry. And actually, it is known that there is a mixed anomaly between the broken symmetry and the solitonic symmetry. Yeah, to be honest, there is no proof of such kind of fact, but for the case of example which I will explain, uh, yeah, we can explicitly check the existence of mixed anomaly. Okay, then I will explain why the twisted partition function must vanish in the case of if a mixed anomaly exists. So we consider partition function with background gauge field for broken symmetry and the solitonic symmetry. And the existence of mixed anomaly implies that if we do a gauge transformation of V, then this is a partition function gets some extra phase. And yeah, here we want to consider not ZAB, but ZA0 because we do not want to consider gauge field for solitonic symmetry. So we choose B to be 0. And D lambda is also should be 0. But even if b equals to 0 and d lambda equals to 0, twisted partition function ZA0 may transform under Lie transformation of B. Because yeah, so the point is that here the expression of anomaly depends on A and B and lambda, and this is not d lambda but lambda. So even if d lambda equals 0, anomaly may exist.
Are
And
these large gauge transformations? The one we're talking
yeah,
about?
we can consider large transformation, but we do not restrict such case. We consider more
Uh,
general Lie transformation.
but isn't this like when you say d lambda equals to 0, even though lambda is not
Uh,
trivial, isn't this an
uh,
example of a large gauge transformation?
I see. So, um, sorry, I'm not sure what the answer is.
Hmm.
Um,
Okay. But
yes,
it
sorry.
looks a bit like it's a closed form, but it's not globally defined. So it's
Yeah,
essentially like a large gauge change, like changing the
mhm.
holonomy.
I see.
But also, I'm not sure. It just looks like that.
Yeah, maybe yeah, it is a large gauge transformation, but I'm not sure.
Okay.
So, and if there exists an anomaly, then it means twisted partition function has some feasibility, and therefore twisted partition function must vanish for consistency. So this is a logic of vanishing behavior uh, from the viewpoint of mixed anomaly. Okay, let us consider examples. First, we consider SSA phase of ZN symmetry, and low energy effective theory of ZN SSA phase is described by BF theory, whose action is as follows. And this theory has two symmetries. First one is the Hooft symmetry of A, and this corresponds to the broken symmetry. And the second one is a Hooft symmetry of B, which corresponds to the solitonic symmetry. And yeah, and this means so this solitonic symmetry is a symmetry of domain world. And yeah, it is known that there is a mixed anomaly between them, and we can calculate the expression of anomaly as follows. And then yeah, from this expression, we find for if A is non-zero, then anomaly appears, and therefore this ZA0 must vanish because of the phase ambiguity. And yeah, this result reproduces the previous result, uh, the vanishing behavior of the partition function in the NSSA phase. Yeah, so yeah, this is consistent with the previous result. Okay, then I will explain human symmetry case. Low energy effective theory of U1 SSA phase is described by compact boson. And yeah, this theory has Hooft symmetry of phi, which corresponds to broken symmetry. And uh, also this theory has winding symmetry of phi, which corresponds to the symmetry of vortices. And there is a mixed anomaly between them. And the expression is as follows. And yeah, we find from this expression, we find for when the A is non-zero, then phase ambiguity appears and partition function must vanish. Yeah, and this result is also consistent with the previous result because, uh, as I explained before, for non-flat gauge fields, twisted partition function must exactly vanish. But for flat field, partition function has finite value, finite non-zero value at finite volume. So this is a consistent result. And yeah, I explained the SS SSE phase of the symmetry and the U1 symmetry case, but this is a known result which I explained before. So I will explain another new example. So let us consider SSE phase of where SO3 symmetry is simultaneously broken to SO2 symmetry. Then in this phase, low energy effective theory is described by S2 nonlinear sigma model, or equivalently CP1 nonlinear sigma model. And the action is given by this. And yeah, of course, this system has SO3 symmetry, which is a broken symmetry. And this theory also has a symmetry of skyrmion. So skyrmion corresponds to pi 2 non-trivial second non-trivial homotopy group, pi 2, so sorry, second homotopy group, which is Z. So pi 2 S equals Z, and the corresponding soliton is called skyrmion. And yeah, it is known that there is a mixed anomaly between SO3 and symmetry of skyrmion, and the expression of anomaly is like this one. Here, this W2A is a second Stiefel-Hoytoni class of A, uh, which is an obstruction of lift from SO3 gauge field to SU2 gauge field. But anyway, so if this W2A is non-zero, anomaly appears, and this means partition function must vanish. So yeah, it is difficult to calculate the partition function of S2 nonlinear sigma model explicitly, but we find this result only from the analysis of mixed anomaly. So I think this is useful. Okay, let me conclude. Yeah, so the summary is as follows, and the outlook of our work is, yeah, so here for the case of discrete symmetry, we consider only gapped phases, but yeah, it is interesting to consider gapless phases and study the behavior of the twisted partition function. And of course, yeah, it is interesting to consider other symmetries like non-invertible symmetry or higher group symmetry. Or so here we focus on non-anomalous symmetry case, group-like symmetry case, but yeah, it is interesting to anomalous group-like symmetry case. And this is a method to detect SSA phase, SPT phase, or yeah, such kind of we we can we can diagnose phases by twisted partition function. So it is interesting to apply this method to numerical computation. And actually, yeah, we are working on this work, and maybe it will appear in this month or next month. Yeah, this is the end of my talk. Thank you for your attention.
Thank you for the nice talk. Now we can have a couple of questions from the audience. Okay, maybe I can ask one question. I remember in your paper you were also discussing SIM-TFTs, and
Yeah.
you were getting like explaining these results from that perspective. Can you briefly explain the idea for that on how
Uh,
SIM-TFT captures these things as well?
okay. So yeah, in symmetry TFT language, so the symmetry of the dimensional theory can be understood by one higher dimensional TQFT. And
Mhm.
yeah, in this case, we consider non-anomalous G-symmetry. So one higher dimensional TQFT is just GL theory with trivial action. And in this case, uh, s- such D plus one dimensional G gauge theory has Dirichlet boundary condition,
Hmm.
and Neumann bound also it also has Neumann boundary condition. And when we consider symmetry TFT, we must impose two boundary conditions. So yeah, because we place TKFT on interval, so we must consider two boundary conditions. One boundary condition determines symmetry of the dimension
Hmm.
theory, and here we impose Dirichlet boundary condition at the symmetry boundary. But yeah, uh, so one another boundary condition is not in general topological, but if the dynamical boundary condition is also topological, then after shrinking the interval, we obtain d-dimensional TKFT.
Okay.
So we can use the symmetry TFT technique for classification of d-dimensional z-symmetric TKFT.
Hmm.
And it yeah, and here how should I say? So yeah, gapped phases. In gapped phases, so in the IR, the system flows to some TKFT.
Hmm.
So
Hmm.
classification of the symmetric TKFT is the same as classification of the symmetric gapped phases.
Hmm.
So we can use a symmetry TFT technique. And
Hmm.
if we put if we impose Dirichlet boundary condition also at the dynamical boundary condition. Which means we impose Dirichlet boundary condition at two boundaries. Then after shrinking the interval, we obtain a full SSE phase, GSSE phase.
Hmm.
And if we impose a Neumann boundary condition as a dynamical boundary condition, then we obtain a trivial phase. And
Hmm.
also, we can consider a twisted Neumann boundary condition. So then, yeah, we impose such boundary condition at the dynamical boundary, then we obtain a SPT phase. And yeah,
Okay.
and we can consider more general gapped phases. Yeah, we can consider more general topological boundary condition, which corresponds to general gapped phases.
Hmm. I
Which I
see.
explained here. Sorry.
Okay. So you also choose all possible topological boundary conditions on the dynamical boundary, the physical boundary, and this
Yeah,
generates you the possible phases like SPT phase, SSP phase, and maybe SET
yeah,
phases.
yeah. CET phase case is little bit complicated. So if you consider 2, 2D as a spacetime, then there is no SET phase because there is no topological order. But
Hmm.
if you consider more higher dimension, like 3D or 4D or something, then there is a topological order, and we can consider SET phase. And
Hmm.
yeah, also, so if we consider, for example, if we consider 3D, three-dimensional theory, then symmetry TFT is described by four-dimensional TKFT,
Hmm.
and the boundary is a three-dimensional. And
Hmm.
in 4D TKFT, we can impose more general boundary condition, which means yeah, as I explained, we can consider Dirichlet boundary condition, Neumann boundary condition for GG theory, but for DTKFT, we can consider uh, Neumann boundary condition uh, and plus some TKFT, and
Hmm.
uh, we gauge diagonal subgroup. Then we obtain new uh, topological boundary condition. And yeah,
I
I think
see.
such boundary condition corresponds to SAT phase.
It's kind of like how people obtain non-invertible symmetries, right? by stacking with the TQ50
Mm,
and diagonal gauging?
yeah, I think so. But yeah, usually, when we consider such kind of thing, we do not use symmetry TKFT. I think,
Ah,
yeah, in such case, we consider only d-dimensional theory and we stack some TKFT and gauging. But yeah, so maybe it is related, but I'm not
yeah,
sure
because
the exact relation.
some people regard SymTFT as gauging the symmetry on codimension -1. Like when you construct
Oh,
non-invertible symmetries, you gauge on the space-time bulk, but then
mm-hmm.
in the SymTFT, you extend your space-time as a boundary to some sandwich bulk, and then you gauge the symmetry over there. So like stacking with a TQFT and then gauging diagonal subgroup is essentially like that, as far as I understand. I'm not sure, but that's how I
So,
understand what you're saying.
I see. I didn't know such kind of things. So
Hmm.
yeah, yes, thank you. Mm, I see.
Okay. Any other question? Maybe I can stop the recording.